But the question is, how can I make this better approximations? How can I get an even better approximation? Well, I guess the next thing that I could do is make sure that I've got some slope. So I can consider another line, maybe with a bit of slope, okay? So maybe make sure that the tangent function is the same, okay, on both my approximation and my true function, okay? So let's make sure that my tangent function is the same. So remember, how do I get my tangent function of any graph, of any function, okay? Well, I differentiate. Okay, so in other words, if I differentiate my true function and stick in x equals 0, whatever that value is going to be, that should be the same as taking my approximation function, differentiating that, and also sticking in x equals 0. So in other words, the tangent function should be the same on both my true function and my approximation function. So let's ask ourselves the question, what is the derivative of e to the power of 2x? What if I differentiate that? Well, okay, isn't that 2e to the power of 2x? Yeah, just a chain rule, so it's 2e to the power of 2x. And of course, I'm sticking in x equals 0. Okay, I'm sticking in x equals 0. Okay, so if I stick in x equals 0, I get 2 times by e to the power of 0, which is just 2 times 1. So therefore, that should just be equal to 2. Now, if I differentiate my approximation function, let's actually come over here for a bit. Okay, so this is my approximation function at the moment. So g of x, I'm basically saying is going to be equal to c0 plus c1 times x plus c2 times x squared, etc, etc, etc. So c3 times x cubed plus c4 times x to the power 4, and so on, and so on, and so on. So I'm now saying that if I want this to be a good approximation, the derivative of this function, when I differentiate it and stick in x equals 0, should be the same as if I differentiate my true function and stick in x equals 0. Right? So what happens if I differentiate this function? Well, are you happy? Let's just consider it term by term because it's just a polynomial. It's easy, right? C0, when I differentiate it, just a number, just goes to 0, right? But what happens to C1 times x when I differentiate it? Well, doesn't that become C1? Okay, so that becomes C1. So let me write that properly, C1, okay? And then what happens to C2 when I differentiate it? Well, that becomes 2 times C2 times x. The power climbs down and the power reduces by 1. So it becomes 2 times by c2 times x, and this becomes 3 times c3 times x squared, and the next term becomes 4 times c4 times x to the power 3, and so on, and so on, and so on. So in other words, this is the derivative function at the moment. Now what I want to do is stick in x equals 0. So if I stick in x equals 0, then surely g0 of 0, well, I've just got a number there, so that's not going to change, okay? Then I'm adding 2 lots of c2 times by, you guessed it, 0. And in fact, every single term after that will always have a 0 in, so therefore it will just drop out to be 0, okay? So every single term after this will always go to 0. So therefore, the derivative of my approximation function at the point x equals 0 is just going to be c1. Okay, it's just going to be C1. So let's come back over here and let's put that back in then. Let's put it back into our table. So we've got over here that the derivative of my approximation function at the point x equals 0 is just going to be C1. Okay. Now remember that I said that if I want this to be a good approximation, this thing should be the same as this thing. In other words, C1 should be the same as the derivative of my function at the point x equals 0. So therefore, I can say that C1, in this case, for e to the power of 2x, that's my true function, should be equal to 2. Okay, so far I've got 2 values of my constants. Okay, I've got C0 and I've got C1. So far my function is looking like 1 plus 2 times x. Okay, so let's come back over to GeoGebra and let's plot this. So therefore, the next approximation of my function, so g2 of x, is going to be equal to 1, and I now know that C1 is going to be equal to 2, and that's going to be times by x, okay? So this looks slightly better, okay? The one in purple looks like a slightly better approximation of my function than my red line did. But what if I want to do even better? Well, hopefully you can see that the next thing up which I can consider could be maybe we've got a point, we've got a tangent, which is just a straight line. Next thing up would be like the parabola. We need to make sure if we try and fit a parabola that it should be the same on my true function as it is my approximation function. So let's have a go at this. What do I mean by parabola? I just simply mean the second derivative, right? So in other words, if I differentiate my function twice and stick in x equals 0, what do I get? Okay, well remember I start with e to the power of 2x, I differentiate it once and I get, so the first derivative, so f dash of x, is just 2 e to the power of 2x. That's what I worked out before. Okay, so therefore the second derivative of my function, should be, well, I bring the power down again. So it becomes 2, sorry, I differentiate my inside function again, it's just a chain rule. So it becomes 2 times 2, which is equal to 4 e to the power of 2x, right? And then all I need to do is stick in x equals 0. So I get 4 times by e to the power of 2 times 0. Well, 2 times 0 is just 0, so it's going to be 4 times e to the power of 0, which is 4 times 1, which is just 4. Okay? Now, if I want this to be a good approximation, I need to make sure that the second derivative of my function, when I stick in x equals 0, should be the same as what happens with my true function. Okay? So let's come over here. Let's differentiate again. Okay? Let's differentiate again. So, if I differentiate again, well, handily I've got the first derivative still stuck up there. So if I differentiate a constant, that just becomes 0. Okay. If I differentiate this thing, okay, now I'm going to write it slightly weirdly because remember that power up there is just 1. Okay, and you'll see why I'm writing it weirdly in just a second. So I'm going to bring the power down, so it's going to become 2 times 1 times c2, okay, times by, well, x to the power of 0, so it's going to be 2 times 1 times c2. And if I consider the next term along, then I get the power gets brought down, so it becomes 3 times 2 times c3 times x, okay, and then if I consider the next one, it becomes plus 4 times 3 times c4 times by x squared, and so on and so on and so on, okay. So let's have a look. Now hopefully you realise here, and you might say, why are you doing that? But hopefully you realise, you'll see it in just a second, hopefully you realise that 2 times 1 is just 2 factorial, right? So if you take a number and you multiply by successive numbers, then that's just the same as doing a factorial. So in other words, if I stick in x equals 0 to my second derivative, then I get, well, it's going to be 2 times 1, so it's going to be 2 factorial times c2, plus, then are you happy that every other term has got a 0 in, it's got an x in. So if I stick in x equals 0, all of the other terms will just effectively become 0. Okay, so that's going to disappear, that's going to disappear, and that's going to disappear. So in other words, what I'm saying is that the second derivative of my function is just going to be equal to 2 factorial times c2. Okay, so it's going to be equal to 2 factorial times by c2. Okay, so let's get rid of that. So the second derivative of my function is going to become 2 factorial times by c2. Okay, well therefore, you've guessed it, if I want my approximation to be any good, this thing has got to be exactly the same as what my true value of the second derivative of my function is going to be at x equals 0. So in other words, I'm saying that, well, I've got 2 factorial times c2 is equal to 4. So if I do a little bit of rearranging, I'm saying that c2 should be equal to 4 divided by 2 factorial, which of course is just the same as 4 divided by 2, or 2. Okay, now just to remember where this came from, okay, I said that c2 should be equal to whatever the second derivative of my function is, the true value of my function is, when I stick in x equals 0, divided by 2 factorial. Remember that 2 factorial came from when I differentiated the approximation of my function. Okay, so that's where it comes from. Okay, so let's go back to GeoGebra and let's see this plotted, because now I've got a new value that I can stick in. I've got 2, which remember is my x squared bit. Okay, so it's going to become 2 times by x2. Okay, so if I go over here, and if I stick in the third approximation of my function, I get g3 of x is equal to, well, I've still got the same thing as before. Okay, so I've still got g2, so 1 plus 2x. Okay, but now I'm adding on, well, my c2, which is 2, times by x squared. Okay, so this is now my next approximation of my function. It looks even better, right? I've got that parabola coming in grey. Okay, I've got the parabola coming in grey. So that looks much, much better because now I get a bit more curved bit action going on. And in fact, if I zoom in a little bit more, you can see that it matches e to the power of x pretty good around x equals 0. I mean, it's rubbish everywhere else, like it's rubbish outside of x equals 0, but close to x equals 0, pretty good. Okay, pretty good. But what if I do want to do even better? Well, what I can do now is consider the next derivative along, which would be the cubic. Okay, so let's consider now the cubic. And hopefully you can see where this is going, okay? So in other words, if I differentiate my function 3 times, now just because I don't want to keep on writing out dashes each time because it looks a bit messy, I'm going to write 3 in brackets, which just means the third derivative of my function, okay? And I'm going to stick in x equals 0. Well, let's have a look. What is the third derivative of my function? Well, okay, the third derivative of my function will just be the derivative of what's up here. So that's just going to be, if I differentiate the inside function, if I differentiate 2x, it becomes 2. Multiply, just using the chain rule, so it becomes 8e to the 2x. Okay, so in other words, when I stick in x equals 0, hopefully you can see it's just going to be 8e to the 2 times 0, which is going to be equal to 8. Okay, let's do the same thing with our approximation function, because of course we want that to be the same as what's happening with our true function with the third derivative. So let's come over here. Let's differentiate it 3 times. So let's differentiate what we had before again. Now hopefully you can see, okay, so that's just a number. That thing there is just a number. Differentiate it, goes to 0. The next thing along, remember this is x to the power of 1. So this is going to become 3 times 2 times 1 times by c3 times by x to the power of 0. So that's my first term of my third derivative, okay? And I get 4 times 3 times 2 times c4 times x, and so on and so on and so on. Now hopefully you can start to see here why I wrote that as a factorial for my previous function. Because when I stick in x equals 0 into here, watch what happens. I get 3 factorial, that's 3 times 2 times 1 times size c3, and then every other term, so this term and every term afterwards, will always have a 0 in, because I'm sticking in x equals 0. So therefore all of these terms are going to disappear. In other words, the third derivative of my approximation function at the point x equals 0 is going to be 3 factorial times by c3. So let's come over here and let's copy that across. Okay, so let's come over here and copy that across. So this thing here now, the third derivative of my function, so g, third derivative of my function at the point x equals 0, will be 3 factorial times by c3. Okay, now remember, if I want this to be a good value, a good approximation, I want this thing to be the same as this thing. In other words, 3 factorial times c3 should be equal to 8. Well, after a little bit of jiggery-pokery, okay, after a bit of rearranging, I can say that c3 is going to be 8 divided by 3 factorial. So if I stick that into a calculator, okay, I've got here a calculator, so I can do 8 divided by 3, and then the factorial is shift that, and that comes out as 4/3. Okay, so in other words, this thing here will come out as 4/3. Just remember where I got that from. Okay, this came from saying that c3 should be equal to the third derivative of my true function, sticking in x equals 0, divided by 3 factorial. Remember, that came from the fact that I had the 3 factorial there. Okay, so let's go back to GeoGebra then, and let's see that approximation action. So here we go. So g4, I'm getting better now. Well, g4 of x is just going to be what I had before, so 1 plus 2x plus 2x squared, okay? But this time I'm going to add on my next term, which is going to be 4/3, okay? So 4/3 times by x cubed, okay? Now you can see there, just about, okay, if I get rid of the other ones, you can see here that I've effectively got that brown function there, that cubic function there, okay? So that is my next approximation of my function. But you can see what happens as I build up my approximations. I'm getting a better approximation, and more importantly, I'm getting a better approximation further away from the point which I started. So I started at the point x equals 0, okay? And after 4 approximations, I now have a function which approximates e to the power of 2x quite a far way away from the point which I started with, x equals 0. Like, think about it, the red function, okay, this one here, only matched my true function at a point, okay? Then I consider the tangent line, okay? Which was this one here, so the purple line. That now starts to match the function a slightly further distance away from x equals 0, okay? So it sort of matches it between maybe x equals maybe 0.1 and negative 0.1, okay? Then I considered the next approximation, which matched it even further away, maybe sort of negative 0.5 and 0.5, okay? Then I considered the next one, which matched it even closer, maybe negative 0.8 and 0.8. Just for the sake of completeness, let's go and do another term, okay? Just to make sure that we can see what's definitely happening here.